Ivan Krstic, I'm not sure if I pronounce his name right.
That's perfect.
Is a head chief troublemaker at OLPC. I'm sure he brought one. I have an XO. A couple other people here probably have one. Ah, there's one. Let's all play the mesh game afterwards. In the meantime, one request. Since this is going to be live on Google Video, and there are actually visitors in the audience, as I think I can see here, please keep your Google confidential questions to yourself, or ask them quietly afterwards, not while it's being videotaped. So I give you Ivan Krstic.
Thank you. Hi. So it's a pleasure to be here. Thanks for having me. In terms of the structure of this, there's a lot of things that I want to tell you about. And I'm going to try and run through this pretty quickly, and then have a sort of an Ask Me Anything segment at the end. So Guido tells me that people here are very technical, and that you guys are going to have technical questions. So I've tried to make the talk technical, and if it's not technical enough for you, by the end, by all means, you can ask questions that are as technical as you could possibly like them to be. We're also, I know a bunch of us are having lunch afterwards, so you're welcome to join us for that as well, and bug me more with questions. So I'm going to super briefly tell you, who I am. I want to, before we get into the technology, I want to tell you what it is that OLPC is actually trying to do. Because there is so much cool technology that we're working on, there's sort of a real risk that when technical people see the project, they just get carried away by the technology, and they don't actually pause to think what it is that we're trying to do, and why does any of this matter. And the project was not started because of the technology. So I'll tell you about how we're actually doing this laptop and how we're building it, and then hopefully I'll tell you how you are building a laptop and helping us out. So my position, in addition to being the chief troublemaker at OLPC, which is a position I'm proud of, I run security. I've been designing the security architecture for OLPC, which I'll talk about a little bit later. It's sort of a pretty different take on security than what most of you guys, I suspect, are used to. And my background is systems. So when I start talking about the GUI stuff, et cetera, I get a little fuzzy on it, and you can probably find questions that I won't completely be able to answer if they're about the graphical sort of soft and fuzzy things. So OLPC came to me sometime in the middle of last year, and in the first 5 minutes of talking to Walter Bender, who's the president of OLPC, he asked me the following 3 questions. First, can you make 100 million laptops secure? Can you rewrite our file system? And oh, by the way, can you make this usable by 6-year-olds? Now, I hear Google has pretty tough job interviews, but as far as job interviews go, I have to say I haven't really heard these kinds of questions before. So I was hooked, but I didn't really know that much about OLPC. I mean, I'd heard about it, I'd seen it in the news, but that was sort of the end of my exposure. So I sort of set out to figure out more what these guys are actually trying to do. Here is the goal of OLPC. It's 4 words, right? Change how kids learn. And you'll notice that the word laptop is sort of conspicuously missing from that goal. Well, change how kids learn. Why? Why bother, right? Most of the people who are here have gone through the normal sort of formal learning process, and we're, for the most part, all turned out OK. Some more insane than others, but in general, we're OK. So what's broken about it, and why fix it? So here's something strange, and normally I have a lot more to say about this. So if you're curious, we can talk about it afterwards. But I'm trying to compress this part here. Here's the weirdest thing that I sort of found about formal learning, right? By the time you're 3 or 4, you will have learned what I call the fundamental principles, and these are the sort of very deep truths that are completely non-obvious if you haven't learned them as a kid. Things like the sun goes up and goes back down, and if you jump, you fall back down, and water is wet and fire is hot. And I mean, these are deep things that you learn as a kid and then never really think about ever again because they're just sort of second nature. But you learn these things by the time you're 3 or 4, And at 5 or 6, you come into school, and the learning process that's taught you everything you know up to that point goes out the window. Just like that. I mean, there's pretty much a literal flag day where it just stops being actual and changes completely. How does it change, right? Well, up until then, until you're 3 or 4, the way you've been learning is you get curious about something. You don't decide to say, well, today I'm going to go and do some learning. You go through your day and you have hundreds of questions and you ask them to parents and friends and peers, and you get answers, and you keep integrating this into your sort of vision of how the world works. And this happens sort of all day, everywhere. When you enter school, this completely changes to the point where learning starts being driven by an authority figure, not by your curiosity. It happens for particular hours. It's unidirectional, and there's one guy like me, basically, trying to impart knowledge on you. And it happens in a particular place. And we know that this can actually work great. I mean, it can definitely work very well if you have a great teacher. If you have a lousy teacher, it works not so well. And if you don't have a teacher at all, it doesn't work at all, right? So this is not a stock photo. This is a picture that we took either in Argentina or Brazil. I forget. But this is a staggering number. There are 1 billion kids of school age in the developing world. I mean, we're talking 1/6 of the entire world population. So what do these kids lack? It's hopefully clearly not ability, right? I mean, I actually get people telling me, asking me things like, well, how do you know these kids are really capable of learning the same way that we all are? And that sounds like an outrageous question to me, but I've actually gotten asked. One way I've come up of trying to convince people that kids lack opportunity and not ability is that if you take China and you rank people by IQ and you take the top 25%, that top 25%, there's more people in there than the entire population of North America. So clearly, it's not going to be a matter of ability. Clearly, it's a matter of these kids not having opportunity. So, I think we can agree that certainly education in the developing world leaves a lot to be desired. At this point, the people who founded the OLPC later said, well, how do we fix it, right? What can we do to make this better? One way you could try and fix this is through some kind of big top-down rethinking of how schools in general are supposed to work, development of some kind of global curriculum, sort of this big operation that, if you're very optimistic, could take 50 to 100 years. I personally think it would never happen. But if you're super optimistic, maybe in 100 years this can happen. 100 years is a long time, right? I mean, think where we were in 1907. Google certainly wasn't around. We are way too impatient, we being OLPC, right? I mean, this was discussed, and people said, well, can't we do something now? I mean, can't we just try and make this better right away? So if we were trying to do this, how would we fix it, right? Well, one thing we'd want to do is try and get peer learning back into the picture. I mean, it worked until you were 3 or 4. It worked phenomenally. It taught you most of everything. Let's do that again. Let's get learning driven by curiosity again. Kids should be able to have some kind of way to get curious and get answers, regardless of whether their teacher can provide them or doesn't know or isn't there. So it was only at this point in the thinking process that laptops really entered the picture. And we said, well, laptops would be one way that we could try fixing things right now and then let schooling in general, schooling, mind you, being very different from education, fix itself over time. So I'm going to dive into the technology, but because I've cut the education part so short, if any of this is unconvincing, by all means, come and talk to me afterwards. So after we decided, fine, we're building a laptop. We're going to do this. How do you build a laptop for kids? How do you build a laptop that kids are supposed to carry around with them everywhere they go, that they're supposed to use in climates like Libya, where there's fine sand and extremely hot temperatures, in places where there's a lot of rain, the laptops can get splashed and wet. You don't want to have to replace parts every 3 months. You don't want the laptop to break if someone drops them. How do you do that? So I'll tell you about the X01 laptop that I know several people are holding. So there we go. So that's the laptop, and we can pass them around a little bit later. So here's what's in those particular laptops, and here's what previously we were trying to ship with. It's a little geode low-power processor running at a watt, 266 megahertz, no L2 cache, a very small amount of L1 cache. We've actually done a significant hardware update. This is pretty recent news in the last couple of weeks. We've gone up to a 433 megahertz processor with massively more cache, which actually speeds up Python about 200 to 300% in certain cases. And I'll tell you a little bit later why we're curious about Python. I mean, why we care about this a lot. But it's now actually quite a reasonable hardware configuration. And because we also jumped from 0.15 micron CPU, which was the GX, to 0.13 micron LX, we can do all of this and use 20% less power. So this is a 0.8 watt processor. We doubled the amount of RAM to 256 megs. We doubled the amount of NAND flash storage to 1 gigabyte. There's no hard drive. There are no moving parts. So our primary storage is a piece of NAND flash that we can wear level in the kernel and make sure that it's utilized equally across the board. And that's a file system called JFFS2. When we say ultra-low power consumption, we really mean it. Our peak power consumption is 4 to 5 watts. The peak power consumption of your laptops go up to 40 to 50 watts. Our standard power consumption, if you're not pegging the CPU, is closer to 1 to 2 watts, and quite a lot less if you're in any kind of suspend mode. We are trying to do probably the most aggressive work in Linux power management of anyone, anywhere, ever. We would like to be suspending this device into S3 every couple of seconds. If nothing on the screen is changing, we want to be suspending the entire machine. That's sort of radical, right? I mean, your laptops take 10, 15 seconds to suspend and resume. We want to be doing this every couple of seconds, so what gives? Well, the first thing you do is you ditch ACPI, and you roll your own power management. And the target we have for power management is suspend and resume at the edge of human perception, meaning we want to be able to suspend in about 100 milliseconds and resume in another 100 milliseconds. How do you do that? Well, you get help from your firmware. We're using something called open firmware. If any of you guys are familiar with Sun machines and OpenBoot, the person who developed OpenBoot 20 years ago is our firmware engineer, and we're running open firmware on our system. So it's a Forth-based piece of firmware. And because it plays along with our power management, we can actually get it to be initializing the devices that take a long time to stabilize in parallel with the kernel initializing a bunch of the other sort of quicker devices. And the kicker is, you can suspend your laptop, even if you can somehow get it to suspend quickly. If you were suspending it every couple of seconds when nothing was happening, you would lose an image on the screen. So we put in a little ASIC that we engineered called the DCON, the display controller, which is basically a hardware frame buffer. It sits in front of the LCD, and we can essentially tell it to freeze frame. The DCON and the LCD sit on separate power rails from the rest of the machine. And so we can suspend basically the entirety of the machine and keep the display active and showing an image. And as soon as you hit a button or move the mouse, in a tenth of a second, we can be back up and running and processing whatever you need us to process. Our display is a dual mode display. It's a technology we invented in-house. It's something that does sort of normal medium resolution color mode. But if you turn off the backlight and flip it into monochrome mode, the effective resolution jumps up to 1200 by 900, which is essentially 200 dpi. It looks like a book. Maybe we'll do some demos for you guys a little later, but it's really quite a thing to see. And the great thing about the LCD is that with the backlight off, it's sunlight readable. So here you see two laptops showing the same image on the screen. And ours is, the cute one. We're pushing the frontier on networking. We're doing mesh networking. Mesh networking is another name for sort of ad hoc, multi-hop networks. And we're one of the first people to implement 802.11s, which is an IEEE draft that is amending. It's scheduled to amend 802.11 and provide multi-hop ad hoc networks running on top of normal 802.11. We have rotating little coax antennae. So if you guys see the laptops and see the little bunny ears sticking up, right? The bunny ears are actually much more than a marketing gimmick. It turns out that when you put up the bunny ears, we get about 3 extra decibels of antenna gain, which is significant. We have a volunteer in the Australian outback who does some wireless testing for us. And so we sent him a bunch of laptops. And the way that he's come to do testing recently is he and his wife each grab a laptop. He sets up his wife's laptop to be streaming music wirelessly to his laptop. And then they turn and face separate directions and start walking. And when he loses the streaming music, when he can no longer hear it, they look at GPS coordinates and figure out how far apart they are. Any guesses as to what the latest numbers are? 2 kilometers. So this is real. I mean, this is not lab conditions, right? This is actual testing that someone other than us has done. It's still a draft. For those of you who are interested in ad hoc and multi-hop routing, we can happy to talk about it more a little later. But basically, it's a very simple amendment. It provides a mandatory routing protocol that's based on AODV. But you can also be using different protocols for this. The standard lets you, as long as you also implement this one. So because we're the first to really be pushing this, we're discovering sort of all the hairy implementation issues that you run into only once you actually deploy something. On the software side, the way that the mesh works is we're using Avahi, which is the free software sort of mDNS responder. But our use case is sort of pushing the author, a brilliant guy by the name of Lennart Pütering, to have developed something that's not mDNS. It's something called Mesh-DNS, and it's a DNS-SD compatible replacement for mDNS that is built especially with the use case of mesh networks in mind. Meaning it scales a lot better. It doesn't run into many of the problems that normal mDNS runs into when you have multi-hop networks, et cetera. And for people who are totally software people and aren't familiar with ad hoc networks and multi-hop networks, here's what essentially our use case looks like. So here is our school server, and this laptop can't hear the school server, but he can hear this laptop, and this laptop can forward packets here, and finally they can reach a school server and go out to the internet in the sky. Yes?
How does this role of the laptops play with the 2 seconds to sleep? Does that thing sleep, and then what happens to my camera?
The question is, what happens, how does this play with the fact that we're trying to suspend our laptops every few seconds, which is an excellent question. And after we triumphantly decided that there's a chance that we can get power management working the way we want to, that was the question that we asked. Well, that's a great idea, except now the mesh doesn't work. So what we did is we're using a unique networking chip in these machines. It's a chip that actually has its own little ARM9 processor on board. It's self-contained, and it can keep running when the entirety of the rest of the laptop is powered off. It contains routing tables and can do L2 forwarding even with really nothing else in the entire laptop functioning. We have all the sort of standard goodies. We have a bunch of USB ports. We can take power from almost anything that produces reasonable DC. Solar panels, car batteries, pull cords, outboard cranks, pedals, you name it. We have stereo speakers. We have a pretty fast VGA camera, surprisingly good picture quality. We can take external storage with the SD card slot in addition to USB drives, et cetera. We have a microphone. Our touchpad is something that's pretty weird. If you look at it, and you can look at it later, it's actually very wide. And the reason for this, it contains 3 segments. The middle segment is a normal touchpad, like what you guys have in your laptops. That's capacitive. You can use your finger on it. But you can use all 3 segments of the touchpad as essentially a resistive tablet. So you can grab a pencil or anything blunt, really, and use the entirety of the wide touchpad as a tablet. And if you're trying to teach kids how to write, you can imagine this being pretty incredibly useful, in addition to sort of all the other kinds of interesting uses you can come up with for that. In terms of batteries, we were pushing the envelope not on how long one charge lasts, but how many charges we can actually get out of the batteries. We don't want to be having to replace the batteries frequently. So we were able to do some pretty significant progress there. But then something interesting happened. A completely new chemistry sort of appeared out of the blue. This is a lithium ferrous phosphate chemistry for batteries. You can't find it on the market yet. And it's looking reasonably likely that we might be shipping this chemistry. I should say the reason this is particularly interesting is it's safer than nickel metal hydride, which is otherwise the safest battery chemistry you can find. It burns colder, and it's quite a lot lighter. I don't have the batteries on me. I did a little show and tell at PyCon, and I passed around the normal nickel metal hydride and then a lithium ferrous phosphate battery of the same size, and people were pretty amazed. I mean, it's almost twice the weight in a nickel metal hydride battery. We have normal audio that you would expect, but we hacked the microphone port to also act as a sensor input port, meaning we can actually read the direct line voltage from the microphone. So for 50 cents or $1, you can build sensors for things like temperature or humidity or light and hook them up directly into your microphone jack and read the sensor values from the laptop and have sort of a little portable physics lab as you go. We're running a Linux distribution that's based on a very stripped down, almost unrecognizable Fedora core. And one thing that became very obvious to us is that we need a machine that is based on open source and free software only. Why? Because what you want to do here is build a glass Lego box, right? You give it to kids, and at first they can play with it and see what's on the inside. But then it gets really interesting because they can take the thing apart and change whatever they want and put it back together and be able to use the things that they've actually changed. So one thing that we were sort of in a brainstorming session sort of thinking about was, well, how great would it be if you had like a button on the keyboard and you pressed and you could see the source code of the software that you're running. And it just worked, right? So that's what we did. So here is our little gear key that is a view source button. And you can actually see the source of almost anything that's running. Now, the problem was that after we put the button on there, we figured out that we didn't really have any idea how to implement this well. Luckily, we suckered Hida into doing it. We figured if anyone is smart enough to do it, the guy that wrote Python probably is. And luckily, he didn't protest too much. So we're still sort of looking to him to help us out here. We have more issues. I mean, drive space on this machine is tight. It's hard to ship the source for everything. Recompiles take a long time. It's not clear we can ship the entire compiler toolchain. So, one thing that also started becoming clear is that you want some way to have the programs that you actually run be the source code, and the act of running should be the same as the act of compiling. And man, if you could only program interactively. The solution is Python. Everything that we can reasonably implement in Python on this machine will be implemented in Python. And I really mean almost everything. We're talking GUI, window manager, presence, communications, system boot, init daemon, security service, platform crypto, file system, search. Basically, almost anything that runs in user space, if it can be done in Python, will be done in Python. There are exceptions, of course. We're not going to be re-implementing x.org in Python, as fun as that would sound. The Avahi daemon is not something that we really want to re-implement. The way we do sound, the way our system bus for IPC works. These are things that are going to stay pretty much intact, and we're not going to be re-implementing that. And when I run through the list of stuff that we want to implement in Python, I sort of mentioned the file system in quotes. And people usually go, huh? You're going to write the file system in Python? And the short answer is yeah. We're trying to do something pretty different here. We're creating a centralized storage for user documents on the machine that's essentially a big object store. And if you do this, you get some pretty incredible things that then the operating system can do for your documents, right? You get version control on all of the user documents that you have on the machine. You get efficient N-way synchronization. You can get delta compression. You can track all the metadata. Really, it's sort of like putting your entire machine under very advanced version control that can sort of do the right thing. And in addition to this, you get sort, filter, and timeline for the things that are happening on your machine. You can ask the computer, show me everything I did yesterday, which you can't really easily do on your computer. But one particularly cool thing is you get pervasive search, right? And this is something you guys should be excited about. What I mean by pervasive search is that the moment something comes into your machine, it's searchable, right? The moment you visit a web page, it's searchable. The moment you open up a file from somewhere, it's searchable. So really, you get search as a much more powerful way of dealing with information. If you know that search will find anything that's on your machine and you didn't have to have an indexing run or anything, then maybe you're not going to be using your file manager nearly as often because, hey, what's the point? The way this is working, by the way, is we're exposing the object store as both a dbus service, dbus is our IPC, and as a little web server that things can connect to and access files. And the cool thing is, what happens is, even though you're interfacing with this central object store for all the user documents, the way you actually operate on files is still Unix semantics. So you still have your open and write and fseek and such syscalls, and the two don't really clobber each other. What I just described, by the way, is called Yellow. We're going to have a tech preview release very soon, and we have open problems with it. Things that are still being solved, things that I'm still working on. Things like smart N-way synchronization for large repositories is really hard. Drop-off, yes?
What happens if I put a fat SD card on the machine?
OK. The question is, what happens when you put a fat SD card into the machine? The answer is you can grow your object store to it. But was there something in particular you were asking about?
But I mean, the semantics of the regular file system are different, right? If I understand you correctly.
So I don't think there's a super quick answer. The best answer I can give quickly is it'll just work. OK? The way that I can try to answer this quickly. Okay, the way that this works is you talk to the object store service and you say, I would like to open a file. The operating system draws a little dialog box. The user chooses a file, and the user can choose a file based on search or anything else. And what happens is the object store will then basically make that file appear in your application's directory space. Okay, so it doesn't matter where it's actually backed. You don't care. The file will always appear in your application's directory space.
So will I be able to read a file that's already in the card? That someone
yes. The question is, will you be able to read a file that's already on the card? And the answer is yes. OK. If you have, so one of the things that we're looking at is, we have limited storage on this machine, and we'd like to do something that we're calling drop-off, which is the idea that we let you star things that you really care about, like you would do in Gmail, to say, this is something that is important to me. But then, if you think about it, right, if you're writing a paper, you'll do, I don't know, 200 revisions in an hour or 2 hours or something. And while you're writing it, you want to keep all of those revisions for things like undo. And to be able to see what you actually did. But then, a month from then, you probably don't care about all 300 revisions. And 6 months down the line, you almost certainly don't care about more than one revision for every hour you spent working on something. So what you'd like to be able to do is for the system to be smart about figuring out basically that the things that you haven't starred, you can sort of drop off when you start getting low on space. And if you've backed them up somewhere, then you particularly don't care, because if you really want it back, you can get it back. But if you don't have backup, you want to be clever about this. For instance, I mean, if the oldest 100 documents are all little text files, but then there is a 6-month-old video that's 5 times bigger than the oldest 100 text files, well, you kind of want to drop the video rather than the text files, right? But it's not clear what the heuristics should be for that. So that's still somewhat of an open problem. If you have ideas on how to do this, come talk to me. I'd love to hear them. Our GUI is it's called Sugar. It's something you can play with today. It's running on the laptops. You can download it. All the sources up, and it's based on technologies that are somewhat familiar. The toolkit is GTK+, but we're not using it to draw widgets. We built our own canvas that lets us draw the widgets. It's called Hippo Canvas. We're using dbus for IPC. And Sugar is a different approach to GUIs. We're ditching overlapping windows. We're going with full screen windows. We want to provide much more context as you're actually doing things and using programs. And we're building collaboration sort of into the operating system. What I mean by this is that network and presence are things that we consider sort of fundamental to how OLPC is supposed to work as an educational program. So there is a presence service that we expose to you as an operating system level service. And what that means is that if you're an application developer and you want to write programs where people can work together, you want to write a drawing program where people can work together, et cetera, it's going to be fairly easy to do this, because we'll give you the APIs where the operating system keeps your buddy list, essentially, right? And applications have access to this, and applications can depend on there being a standard for what presence means and be able to use it to do collaboration, et cetera. And because all of this is based on completely open stuff like XMPP and Jabber, you can do neat things like mesh extrusion, right? Which means if you're part of a mesh in say, your village, but then maybe you go away for on a field trip somewhere, or maybe maybe someone comes and visits your village for a couple of months and then goes back to their country, they can actually join the mesh sort of remotely, which has some really nice implications. So this brings us to what I've been spending much of my time on, which is security. So security for OLPC is sort of a very different ballgame than most security that people who do security are even used to. I'll tell you in a second what the sort of the couple of things that constitute security for us. But one thing that should be obvious to you guys is that if we succeed, and we're putting in 5 to 10 million laptops out there this year alone, possibly up to 50 million next year, we are creating one of the largest computing monocultures in the history of computing. And there are several sort of doomsday scenarios that you really don't want to see come to pass. Certainly, you don't want someone who dislikes OLPC, and there are plenty of people who dislike OLPC, being able to write a worm and kill 10 million laptops for kids that are using them to further their education. You guys in particular don't want to see someone writing a worm that DDoS's Gmail, right? I mean, and once you have 50 million machines connected from all over the world, well, maybe that's a real threat. Maybe it's not for Google, but it's going to be for almost anyone else, pretty much certainly, right? So we're taking security very seriously. We're probably the only project that I know where a vendor that's trying to make mainstream mass-produced computers in large volume is actually willing to prioritize security and say, this has to be done securely from the start. So I was involved as a security person from essentially the get-go of the project, which doesn't happen very often. So let me tell you what security is for us. We have parts of this machine that are hardware, but you can damage it from the software to the point of requiring hardware replacement or repair. 2 chips, right? The NAND flash, which is primary storage, has a limited number of write array cycles. If you run it down, that machine is not going to be doing anything until you replace the NAND flash. The BIOS chip is rewritable. because you want to be able to do BIOS updates. But if someone overwrites your BIOS chip with a string of zeros, you're not going to be getting very far booting. So that's sort of the first thing we want to do. We want to provide recoverability and openness. So we're going to this effort of saying, well, we'll have a view source button on the keyboard because we want the kids to get curious and be able to change things, et cetera. But it's very easy to say that and leave it at that. And what will happen is the first time someone screws up their machine because they've edited a piece of source and deleted a bunch of lines, and their machine now either doesn't work or doesn't work as well or doesn't boot, if the kid has to now take this computer to an authority figure of some kind and say, well, mea culpa, I screwed up, please do something so it works again, and they get yelled at for damaging their expensive laptop, et cetera. I mean, kids are pretty quickly going to not really feel free to experiment with their machines anymore. So you have to be open. You want the machines to be open, but you have to be recoverable in a way that doesn't really depend on other people, right? You should be able to screw up your machine for any value of screw up that doesn't involve a soldering iron, essentially, and be able to get back to running state. We want to prevent permanent data loss, which sort of goes hand in hand with this, because if all we can tell you is, well, we've built a mechanism in so that if you screw up your machine, you can press some buttons, the operating system will get restored, but all of your data is gone, right? It flew out the window, then that's sort of the same kind of disincentive for experimentation. And we're trying to fix this. And this is one part where Google comes into the picture, because the rumor is you guys are pretty good at storing big amounts of data, right? Huge privacy issues, right? Kids as young as 5 or 6 in front of machines with microphones and video cameras. You can sense any number of potential disaster scenarios here. And it's absolutely critical that we sort of go out of our way to make sure that privacy is protected. We want to make sure that it's difficult to use these laptops as a platform for attacks. You can't, as long as you're providing this much openness to the users, you can't really prevent them from being used as an attack platform. But you can do things that make it so that they're not very attractive if you're trying to launch massive DDoS attacks, or if you want to inform all the kind Google people of the deposed dictator that left a large cache deposed with his general, et cetera. So, which is, mind you, something that gets brought up quite a lot since Nigeria is one of our launch countries. And one of the most controversial things is we want to keep the laptop under control of its owner, meaning both that we would like to make sure that software can't do things that the user doesn't want to have happen, but it also means that these laptops should not be an attractive target for theft. You really don't want tens of thousands of these being stolen and put on eBay. So this, to start with, is really hard. I mean, I was mildly depressed after putting together that list for the first time, and then it got worse, right? So our goals while doing all of this security-wise is we can't have passwords. These are 5- and 6-year-old kids. They don't remember passwords. It doesn't work. You can't expect them to read. A, because they might not be able to read yet, and B, because if all the security system does is put a dialog box on the screen that expects you to know the internals of TCP/IP and how your machine works to be able to make an educated decision as to allow or deny something, that's not actually protecting anyone, right? It's maybe protecting the vendor legally, but it's not actually getting anything done. You can't depend on massive amounts of updates being pushed to machines on a frequent schedule. You might not have connectivity. When you have connectivity, you might not have a lot of bandwidth. Right now, my favorite Linux distribution, which is the same one that you guys use, if you install their latest long-term support release from CD and you connect to the internet, it'll happily tell you that it has to download 316 megs of security updates. Right? That's not something that we really want to do for these 10 million machines and 50 million next year. You can't, well, you can, but we're not going to, depend on secrets in hardware or in software to do any of this, right? We're not going to do security by obscurity. It's simply not an option. And finally, we're not going to lock the machines down, right? A lot of the machines that are sort of the managed and embedded machines, they only let you run software that their vendor signs cryptographically. And you've heard my position on the educational value of this project and what we're trying to do. Clearly, that's not an option, right? I mean, we're not going to be locking these machines down. So we built something new. It's called bitfrost. You can find the complete specification on our wiki. There's a Wikipedia article that links to the specification. And there's a big shift here in that instead of trying to make sure that untrusted code never runs, which is what antivirus software and anti-spyware tries to do, we actually try to protect the system while under the assumption that any code that's running could be untrusted and malicious. There's 48 years of capability systems research on how this works. And the way that we're actually implementing it is real virtualization in the OS. So each application is essentially running in its own VM and only has the permissions it needs to get the job done. The interesting thing is that if you have this approach, the definitions of what virus and spyware mean no longer really apply, because if all you can see as an application is your little application space, then if you're a virus, what are you going to infect, right? There isn't anything else in your application space than you. And I'm necessarily glossing over some of the technical details. I'm happy to talk about them or see the spec, because I'm trying to move quickly here. But what this comes down to is we're protecting against hardware damage by doing some pretty clever token bucketing on the NAND flash. We have crypto protection for the BIOS. We can restore the entire factory system just by an operation that is essentially regenerating some links on the file system. We can do that restoration without keeping a separate partition that contains the OS image, by the way. So we're not actually paying a price to be able to do it. Because all the data lives in a centralized store and is revisioned, we can do trivial backups that actually work, right? We can get backups to the point where as soon as you come in range of a server that you don't even necessarily have to trust, all that you care is that it says, I provide backup service, you can start dumping encrypted backups to it and get them back later. And the user doesn't even have to be involved with this process. We're putting in LEDs that are actually wired in series in the hardware with the microphone and the camera. So even if the kernel is compromised and the firmware is compromised, you will actually be able to see a soft glow telling you that the microphone and camera are on. And if that happens when you're not expecting them to be on, you'll know that something's up. The way this works, very briefly, is there's a big kernel patch. It's 40,000 lines of code, but that covers every architecture that Linux builds on. So it's actually quite a lot smaller for just x86. It's something called vServer. It's an existing patch. It was built for ISPs that want to offer sort of virtual Linux servers to customers. And I'm twisting it to do something that it's never been used to do before, which is do desktop security. And so we're putting in a bunch of code, adding a bunch of code to it to let us do some of the things that we care about. The interesting thing about this, by the way, is people are terrified of how are you going to do virtualization on a 466 megahertz CPU. Turns out that with Linux vServer, the overhead you pay is 32K per task struct, but there is 0% measurable CPU overhead with up to 65,000 virtual machines running. I'll let that sink in for about 2 seconds. Right? It lets us do full network stack isolation. It lets us completely isolate the file system. It lets us do this copy and write mode with just a twist on what immutable links do, so we can actually do this at no overhead on the file system. It provides various hooks that we can use. We can add scheduler bias for system services, et cetera, on directly in the kernel. There are no policies with this, so the mental model is very simple. We tell our application developers, essentially, the mental model is you are the only application executing on the machine. And you can use a number of the interfaces that we provide to interface to the rest of the system, but essentially, you are the only application that's running on the machine. one of the things we do is we have these immutable application bundles, meaning that installation is essentially dropping one file into the directory tree, and suddenly you've installed the entire program. And the application, when you do this, only gets 3 writable directories, a temporary directory, a configuration directory, and a data directory. So the application can't change itself. It can't change its own binary. You get some nice security benefits out of this. We have a system-wide update service. And we can do atomic file system updates when we want to update the core operating system. We want to have that same system service doing updates for the individual applications. We don't know how exactly that should work yet. Still somewhat of an open question. So I want to very briefly tell you, I've told you about a lot of cool technology. I want to tell you where things are right now. Most everything of the hardware that you've heard about is done and works. Certainly, it works in the B2 laptops. B3 laptops are entering production, I think, today. And the B3 laptops have the hardware improvements that I was telling you about. Sugar, which is the GUI piece, it works, it runs. There's a lot of work left here to implement our entire human interface guidelines, which are available on the wiki. And the guidelines keep evolving, which sort of makes it very much of a moving target. Our bulletin boards, which are sort of our shared spaces, the idea that this entire room could open up their laptops, we could all connect on the mesh and have a single space where we can put objects and work on them, et cetera. This is we have some preliminary design. It hasn't been implemented yet. On the security side, the kernel patch is ready to be merged, but we haven't merged it yet. Because the power management work has been dominating the kernel work. The user space work hasn't been started because it basically is blocking on the kernel patch being merged. The tech preview of Yellow, which is the centralized object store, is just about ready. It'll probably go live in a matter of days. There are parts of this that are really hard. Yellow is something that I've also been implementing in addition to the security. And there are parts of this, like the synchronization, like the smart tuning that I've mentioned in terms of drop-off, et cetera, like being able to do smart caching, that are still very much open questions. And I keep sort of churning out designs and trying things, but I'm sure we can get it a lot better. In terms of the kernel, suspend resume work today and take about 233 milliseconds. We want to have that. Firmware work, there's plenty of it remaining. We need to integrate some of the crypto stuff that we need. There's a lot of the power management work is happening in the firmware because there's no ACPI. Tons of profiling and optimization to do. It gets started pretty frequently, but we don't have people who are just performance people on the team. So every time that some other fire pops up, the people get sidetracked into helping out with that. So that gets interrupted a lot. The server side of things, our school servers, just now started. There are a bunch of software needs we have here. Something that's fast and sane with multicast as a web cache. And there are some people who are maybe going to be working on that. That hasn't really been started yet. Lots of work with Python. Python is memory hungry. The Python community, there are a lot of people who care about optimizing Python, but there are people who generally care about optimizing CPU, meaning runtime performance, not memory footprint. And it turns out that we're not alone in really wanting a memory leaner Python. Nokia has this issue because they're actually trying to put Python as a plugin language on their cell phones. And the Symbian kernel doesn't do copy on write for memory pages. So they can't even do the trick that we can do, which is run a Python interpreter in the beginning and then fork it off when we need to start activity, applications. Which for us on Linux, of course, gets copy and write going and a bunch of pages get shared, and so it's not as bad a memory hit. They can't even do that. So this is something we'd really like to see happen. More Python. We would love to be able to do some of the more sort of small talkish and Lispish things, like being able to interrupt a running program when it hits an exception, change code, and continue from where it started. This is something that I understand we can't really do with Python right now because the stack gets unwound completely, et cetera. So it's something to look at. I mean, maybe it's doable. Canned modules. The idea that you would be able to load the module and look at the objects that that module created at initialization and basically serialize all of that so that when you're loading the module the next time, you can just sort of load the memory image instead of actually rerunning the initialization, is something that we're also looking at. I think the Nokia guys are actually working on implementing this. Plugins are something that we deeply care about. We think they're one of the only promising ways at this point to manage software growth. And there are no good standards on how plugins should be designed and how software should be designed to accommodate plugins. And it's something that would be really nice to have for the wider community, not just for OLPC. Lots of questions about how plugins should work with security. So I think we're really we're working with a set of pretty fantastic technologies. There's a ton of work that needs to still be done here, and we're shipping in less than 6 months. OLPC, I think, is proof that even in 2007, there are people who deeply care about the fact that there are other people who care about writing beautiful and clean code. Really, this will matter to 10 million kids this year, and it might matter to 50 million kids the next year. And all the technology aside, we think that what's going to happen if OLPC succeeds is there's going to be a generation of kids globally that are going to grow up with access to knowledge and learning in a way that really has never been the case in the history of the planet. This is a really dangerous idea. And I don't think I have to explain why, although I'm happy to talk about it. But it's also an idea that we think has to happen. So in closing, one of my favorite quotes is Thomas Edison, who once said, "Hell, there are no rules here. We're just trying to accomplish something." And I think that's the best summary of OLPC that you'll find anywhere. So if all of this strikes a note, please come, help out. We have a development live CD available now with Sugar and all the development tools that you can just download and run either in Parallels or QEMU or on a separate little machine, and you can help out that way. We can get you laptops if you want to be helping out with any of the hardware work or the kernel work. All of our code is free software. It's public. It's on dev.laptop.org, along with our entire list of bugs. There are no private bugs. There is no backroom water cooler bugs and secret discussions in OLPC. We're completely transparent. And one thing that we have very little people from Google helping out. And the reason I find this troubling is because I see two explanations for this, right? One explanation is that you guys simply don't know that we're doing all of this, or have found it too hard of a barrier to entry. Or that collectively, you guys as some of the smartest people anywhere in the world have decided that what we're doing is so completely wrong that you don't even want to get anywhere close to it. And if either is the case, I would really like to hear about it. So again, please do help us. I think we can get you hooked up with really exciting things to work on that'll also make you feel good about what you're working on. And we have lunch afterwards. Come up, talk to me, or use any of the resources that I mentioned, our wiki, our dev site, or find us on IRC and help out. So thank you. And I'm happy to, I think we have a little bit more time. I'm happy to answer questions about anything, including why the sky is blue, but OLPC questions are preferred. So thanks. Yes? Thank you. Yes?
So I'm curious to hear about your initial reaction when you handed this to kids.
Mm-hmm. So the question is, what happens when we handed this to kids? The first thing that happened is that the adults who handed it to the kids got really frustrated because we have not found so far a single adult who can open up one of these laptops in less than a minute. And we have so far not yet found a kid who can't open them in less than 30 seconds. Right? Past that, you better sort of give 5 hours to the kids and go away. The kids dive right in. The GUI, which is unfamiliar to all of us that grew up with normal GUIs, it takes them 5 minutes to figure it out. We have a music program that lets you play with all sorts of samples and play the piano and whatnot. And you better have a soundproof room when you give the laptop to them, because kids will just bang away at this for hours. So far, we've been exceedingly pleased with what we've seen when we've actually handed the laptop to the kids. And there's a story just yesterday in CNET about actual classrooms in Nigeria getting test laptops for the entire classrooms. And you can find pictures online at, I think it was CNET. And you can see, the kids are ecstatic. Yes, in the back.
So, this seems very exciting from an education perspective,
okay.
From sort of enabling kids. But I guess I haven't really heard anything about how. It seems like there's also a need for adults to use this technology, and you're rolling these laptops out in areas that adults may not have as ready access to laptops or to machines. How are you going to prevent parents from stepping in and saying, well, I'm going to use your laptop instead of letting you use it?
Okay, so the question is, how do adults come into play? And more specifically, how do we keep parents from just taking the laptops away from the kids? There are a couple of answers to this. The first sort of unofficial subtitle to one laptop per child is one laptop per teacher as well, right? So teachers will also definitely have laptops, and we want to get them involved and have them see that this is something that's important. We want to exercise a lot of sort of community and social pressure on parents to not take away the laptops. And we've seen that this works, not just with OLPC. There are places like Extremadura in Spain where, admittedly, it wasn't laptops that were used. These were desktops. But there was a lot of resistance initially to sort of the disruption that the introduction of many computers in schools created. And after a while, because of the social pressure and the community pressure that was exerted throughout the state for parents to really understand that this is something that's important to their kids, the story came around completely. It's now up from principals and parents and everyone sort of being really afraid of this and not wanting it to come anywhere near their kids, to it now being sort of a matter of pride for principals and schools and parents that their kids are using computers, et cetera. So we know this works. And we're hoping that we'll be able to do the same.
I guess my follow-up would be also, how do you prevent families from selling them in a time of crisis or a time of,
The question is, how do you prevent the laptops from being sold? There is an anti-theft system in this laptop. If the country chooses to use the anti-theft system, these laptops are going to be pretty hard to sell. I'm happy to explain more about how the anti-theft system works maybe over lunch. Yes?
Sell to everybody or just to countries that then have to funnel that from their educational system or whatever?
The question is, do we sell to anyone or just the countries? Right now, just the countries. One thing that surprises people when I talk to them about the OLPC is that the core team at OLPC, the people who actually sort of designed most of what you heard, it used to be a 12-person team. It's now up to, I think, 14 people. But that's tiny, right? We're essentially reinventing a computer with 14 people. And part of the reason we've been able to do it is because we've done it with so few people. We've been moving very quickly. But it also means that if you want to handle logistics, it's a lot easier handling logistics for 5 crates of 1 million laptops each than it is to handle logistics of 5 million crates, 1 laptop each. Right? So it's just right now, it's just a matter of us not having the time and energy and people to be able to do logistics for smaller orders. And it's something that hopefully will change in the future. Yes?
You mentioned that you'd like to be able to do sort of more of the types of things that you can do, say, list for small talk, with being able to dynamically change things. So it made me wonder why you didn't pick something like list for small talk, which have a history of dynamic, highly performant systems, including list machines and small talk machines that are close to the...
Right. So, interestingly, if you... I'm sorry, the question is why not, because we want to do more Lispy and small talky things, why not just use Lisp or small talk? And what about Lisp machines and things like this? So if you guys have paid attention while I was saying that we really want to implement as much of everything in Python, that comes very close to sort of the general Lisp machine idea. Now, we're not running Python on the bare metal as Lisp machines did with Lisp, but we're coming pretty close to it. I mean, if you take away the kernel and you look at everything else, you're essentially given a complete Python, everything is Python. We are also shipping Squeak on these machines. So there is a Smalltalk implementation that's going to be available. But I think right now, for any number of reasons, such as size of the community, momentum of the community, I certainly think Lisp, for instance, has a much higher learning curve, a steeper learning curve than Python does for kids. There are a lot of the same reasons apply to Smalltalk. I mean, I really think that right now, the best thing we can do is use something like Python. Yes? Oh, I'm sorry. Pay no attention to the man behind the curtain, who is informing me that we're done with questions. So join me for lunch if you'd like to talk more. Thank you.